This is my multi-toolhead, multi-material 3D printer. It's a Voron 2.4 using the StealthChanger system. 6 tool heads with under 5-second tool changes. Most of the components for the ToolChanger build have been modified or designed from scratch, and I'll go over them in this video. I started this build before there was any commercially available tool or hot-end changers, and I didn't like the waste of AMS systems. When building it, I prioritized performance, maintainability, auto calibration, and aesthetics. It is a color printer, so I leaned into that with the CMYK color palette, plus white and gray to round out the 6 tool heads. It's entirely made of 3D printed parts and off-the-shelf hardware. I did the initial build with 2 tool heads to test out what worked before expanding to the full 6. After testing different combinations, I settled on a Dragon Burner tool head with a Sherpa mini extruder and a TZ 2.0 V6 hot end. This combination produced good quality prints while being budget friendly. I stuck with the mechanism from the tap changer style dock on my initial build, where the tool head attaches to the dock by hooking onto 2 screw heads. With this mechanism, I've never had a tool change failure during a print. I had the idea to use a clear acrylic panel for the main dock structure, giving full visibility to parked tool heads. So I designed a 3-part dock with 10mm acrylic for the main section. By now, you've probably noticed that the final docks were not clear. During the design process, I did some test cuts on the laser to make sure that the docking screws could mount securely without cracking the acrylic. A few days later, after finishing the dock design, I went to cut it out, but the laser wouldn't fire. After some troubleshooting, I discovered that the laser tube had cracked. Thanks to an unheated garage, a record cold winter with over a week below freezing, and my assumption that water would be fine, and adding antifreeze to the coolant lines was overkill. Hence the pivot to the see-through honeycomb docks, which I'm pretty happy with, especially how the LED light diffuses through them. When designing the docks, I put a few extra mounting holes on the bottom because I wanted an attachment point to add a silicone brush. With my initial build, there was sometimes an issue with longer prints where some plastic could build up on the nozzle that could hurt the quality of the print. So I thought it would help to add a silicone brush in the docking pathway that would automatically clean the nozzle every time a tool was docked or undocked. Next, I needed a plate to be a connection point for the filament guide tubes, the CAN bus cables, and the umbilical guide springs to come from the back, inside the printer, and to the tool heads. Besides a reliable connection, my main goal here was ease of maintenance. I wanted to be able to quickly detach all of the connections in case I needed to troubleshoot a cable or swap out a filament guide tube or do any work on the tool heads. I found these 4-pin GX12 connectors that fit the bill. For the filament guide tubes, I started with quick release pneumatic fittings. I found a size where the PTFE tube could go all the way through for a low friction coupling, with an M6 threading that could mount directly in 3D prints. And then I modeled a bracket around these components. In the first version, I designed a curve in the filament path so that the filament could come straight in the back, allowing clearance down here for the wires to the electronics, and then curve up to start the arc toward the tool heads. Unfortunately, the curve added noticeable friction in the filament line, so I needed to redesign. I found a lower profile quick release called the ECAS-04. These press fit, which make them easy to mount. The only downside is they can't be easily removed. Since these are lower profile, it allowed for a straight low friction filament path, while leaving plenty of clearance for the wires. Next up is the umbilical cables. The goal is to have enough structure to keep them organized so that they don't get tangled, and enough flexibility to easily reach all areas of the print bed. The main parts here are the CAN bus cable that I made from USB-C cable that had thick gauge power wires, standard PTFE tube for the filament guide, flat spring steel for structure, and custom brackets to hold them all together. First, I tried an open source bracket design. These were designed to grip firmly onto all 3 elements, resulting in a cable that was too stiff. I designed my own brackets that clamped firmly onto the CAN bus cable to maintain the spacing and orientation of the brackets, but had enough room for the filament guide and the spring steel to move freely. This helped a lot, but I still needed more flexibility. The solution I came to was just having spring steel at the beginning and the end of the cable. This resulted in the best balance between structure and flexibility. For the spool holder, I wanted it to fit the width of the printer, to be easily accessible, and easily enclosable, so I could also use it as a dry box. The printer is just 18 inches wide. I needed as little space as possible between each spool, and adjustability because not all spools are the same size. It's built around 2 rods with roller carriages that can slide along their length. The frame is made from 2020 aluminum just like the printer. It has guide tubes and quick releases. I plan to add panels later to seal it off, along with some desiccant or a dehumidifier. But for now it works great, and it's very flexible for fitting different size spools. The last thing the printer needed was nozzle offset calibration. Since each tool head is not identical, any small offset in the nozzle will result in bad prints. In the initial build with just 2 tool heads, I used a calibration print like this, where you print it, measure the offsets, and manually set them for all 3 axes. For 2 tools, that's okay. For 6, it would be a nightmare. I considered a nozzle camera or a nudge probe, but ultimately went with the sex ball probe. You need to make sure the nozzle is clean, so I designed a mount for a silicone brush. Now with one button press, each tool is automatically picked up, gets its nozzle cleaned, probes the ball from different angles, then the offsets are automatically applied for accurate multi-tool prints. Sometimes a bit of plastic survives the cleaning like you see here, so I need to improve the cleaning routine a bit. But overall, it works really well. Next, I optimized the tool change time. Here's the before and after. This came down to how fast I could push the speeds before the motor started losing steps or the docking became unreliable. I was able to significantly speed up the Z velocity up to the docks, the X and Y velocity between docks, and the speed at drop off and pickup. This, along with increased acceleration and streamlined docking paths, got the tool change time down to less than 5 seconds. Here's a few things I printed so far, a few test prints, some toys for the kids, an enclosure for a filament color sensor, as well as some new projects. Feel free to subscribe if you'd like to see when they're posted. If you're interested in making any of these parts yourself or just want to check out the models, I shared everything on GitHub, including the toolhead dock, umbilical backplate, brackets, the spool holder, the cowl, and the nozzle brush mount. You can find the link in the description of this video. Thanks for watching.